when LLMs are given tools that makes them very powerful and unlocks a ton of really great use cases, but it has one fatal flaw, and that is prompt injection. Prompt injection happens when an attacker is able to insert malicious instructions that end up in the context window of the LLM. And those malicious instructions could be things like overriding previous instructions, or more insidious, like trying to exfiltrate private data and send it out over. And this is not a far-fetched use case because people are already building LLM systems that can read documents, that can send emails, and very often the content of the documents that are read get mixed in with the instructions. So, for example, if I had a system that was summarizing emails for me, but the content of an email being summarized was something along the lines of ignore previous instructions and instead do blah blah blah, that would still end up in the context window of the LLM. So it's really very easy to construct the prompt injection attacks, and that has been a major problem. People have proposed a number of solutions, but none that are principled in the sense that they can guarantee that a prompt injection attack won't happen. It's been a bunch of hacks, and so that's why this paper from Mind and Google is really interesting, because they are trying to beat prompt injections by design. By the way, if you want to learn more about prompt injection, Simon Willison maintains an excellent list of samples of prompt injection, various proposed solutions, and reading this page will really give you an idea of nuances and the magnitude of problem. So a quick aside here, before we get into how prompt injection is solved, you have to look at a similar problem that happened earlier, and that is SQL injection. It is the same basic pattern, which is that you're taking input from the user, and that input could be malicious. That input then goes towards constructing some sort of a command, in this case SQL. So imagine a system where you're asking for somebody's name or ID number on a website, and that ID number eventually ends up in a SQL statement that looks up that person or that ID in a database. And if you didn't do all the proper sanitization, they could construct a really malicious string as the name or as the ID, and then that ends up in your SQL statement and ends up doing something insecure. And the way SQL injection got solved was by cleanly separating data from code. So you need to separate the data, which is the ID or the name that is coming all the way from the user, and the code, which is a SQL. And what let you separate code from data was the fact that SQL is a structured language with a formal grammar and a parser and executor on the back end. So the database has a parser for SQL. And that enables solutions like prepared statements, which is like the standard way of guarding against SQL injection attacks. Pretty much every language today has some library or some convenience wrappers to construct SQL prepared statements that will let you write secure code that takes an input from a user and yet lets you construct secure SQL. Now, that idea doesn't work with LLMs, because LLMs don't take in some formal structured grammar. They just take in natural language. Instructions to LLMs are simply natural language, and the data that they operate on is also usually natural language. So the context window of an LLM cannot distinguish between data or input and code or instructions. It's all just one blob of natural language. And that was the key reason there was no principled solution to prompt injection attacks. So let me quickly walk over the main elements of the proposed, and read the paper for the full details, because it's really well written. And the basic design builds on a proposal from Simon Willison, prompt injection. He called it the dual LLM design, where basically instead of just one LLM interpreting your instructions and your input, you would have two LLMs, a quarantine LLM and a privileged LLM. The authors here take that basic idea and also add the notion of having security policies and capability. Because really, you can't design and build a secure system until you have some way of specifying the policy that you want to enforce. So let's look at each of these pieces. The quarantined LLM, as the name implies, is an LLM with very limited capabilities. Notably, it cannot run tools, and its only job is to take in some unstructured data and some instructions for how to analyze or understand that data and then return structured output. So for example, I could give it a long blob of text and ask it to extract all the emails from that text or all the proper nouns or something like that. And so this quarantined LLM is only doing very narrow, very well specified natural language to structured data tasks. It cannot run any tools at all. The privileged LLM, on the other hand, is able to run tools. And what it's doing is it is writing Python code to invoke those tools. And one of those tools that it can invoke is this quarantined LLM. It's just another tool in its arsenal. Now, this part is really important. The privileged LLM is the thing that is given user input, and it interacts with that user input, but it cannot do anything with the data returned by the tools or by the quarantined LLM. So that data is stored separately in special variables, and the privileged LLM never looks at the contents of those variables. And the remaining elements of this design all come together to make the resulting systems. Like I said, you need a place to specify your security policies. The policy is basically saying how you can call tools, how and when you call tools. The other part that enables you to actually enforce these security policies are capabilities. The important thing to know about capabilities are that they are basically tags assigned to all this data that track the source of the data. And that lets you differentiate between data that can be potentially malicious versus not. And finally, orchestrating all this stuff is what they're calling their camel interpreter. So it's calling the quarantined LLM, the privileged LLM, and managing all these policies and capabilities. They have this nice example in the paper where they go through what the system does with a typical query. So imagine you have a query like this: find Bob's email in my last email, and then send him a reminder about. So my last email is untrusted data. And look at how the privileged LLM breaks down this user query into tools. So this is the standard LLM tool calling mechanism, where you take a high-level natural language query and try to break it down into a series of tool calls to accomplish that. So it's getting the last email, and then it's asking the quarantined LLM to extract the email address from the contents of that email. So note that only the quarantined LLM ever sees the contents of the email, and this quarantined LLM cannot invoke any tool. And now that it's extracted the address, it will send an email to that address. And then here you have security policies which say something like, getting my last email is always allowed. So maybe when I set up the system, I go through some configuration where I say, okay, you have permissions to read my email. And then when you're sending emails, I have a more restrictive policy. So here they're saying it's only allowed if the recipient is trusted. Or you could have a policy to actually ask a human every time you're sending an email. So this is a really principled way to essentially impose a separation of code and data on an LLM system. And the basic idea actually goes back to what things like Perl did back in the early days of the web. So back in the 90s, when the web was first coming up, a lot of web apps were made with something called CGI, Common Gateway Interface, and they were written in Perl. And Perl had this really cool notion called taint mode. And taint mode is doing the same basic thing where it's trying to track the provenance of the data that the application is working with. So it can track if a string came to the application from user input, like a form on a web page, and it doesn't let those tainted strings affect something like arguments to commands that you're then running on your backend. And you would have to explicitly check and mark tainted data as untainted before you could use it to construct a command or a SQL statement or something that actually carried out an action or executed something on your system. So this is kind of the same idea. So that was a quick look at a paper that proposes a first principles design for how to defeat prompt injection in a guaranteed manner. And this is a really great step forward because prompt injection has so far been a huge problem for using LLMs with tool calling and AI agents in sensitive production contexts. So I think people will be adopting this pattern in those kinds of use cases. I hope you enjoyed that. If you like content like this, please like the video, consider subscribing, and I will next time.